Thanks so much, everyone, for joining. So this is our day 7 of our this seminar that we're having, and then I'm very happy that we have Jenny as our guest lecturer today. This is our first and only guest lecturer in this course, and then we're very excited to have you. My brief introduction of Jenny here. So Jenny is a great friend and our collaborator. She is a developmental psychologist and also a learning scientist who uses a variety of methods to understand the mechanisms and cognitive processes that involve in mathematical learning and development. She's currently an assistant professor of early childhood education at the Education University of Hong Kong. Before that, she was Worcester Polytech Institute in the US as a postdoc, working on this from here to there platform, and has many publications out of this project, which is very inspiring and amazing. And before that, she did a PhD at the University of Minnesota. Feel free to add more at the beginning or whatever you like. But yeah, we can get started.
Great. So thank you so much for having me to share my work with you. And thank you so much for Tomo for inviting me. So today I'll talk about some game-based learning technologies that I've been working on, and then some thoughts about design considerations when you are thinking about designing your own tools, and then some potential research collaborations that you could also think about. So here's a little bit of my information, and I'll also talk a little bit more about myself, just so you know what my perspectives are and like my background and where I'm coming from with like my thoughts and comments. So for today, I'll talk a little bit about my research, the big picture of my research program, and then we'll go into more details about 2 studies. Some of these papers you may have read, and I've read your comments already, and they're all super insightful and very exciting, and looking forward to talking about them with you. So for the first study, I would like for us to think about potential design features that support algebraic learning. And then for the second study, thinking more about using the log data within the tools to explore students' cognition, including their problem-solving strategies. And then I'll open it up for questions and discussion. So for my research program, like Tomo said, my background is in psychology, developmental psychology. And then so my thinking is really rooted from the psychological and developmental perspective. So what I often think about is the cause and effect of human thinking and how these thinking change over time. And then with my postdoc experience in learning science and technologies, I also think about how psychological research and developmental research can contribute to and be informed by the work in learning technologies. And then so here's a big picture of my research. What do I think about? So I think about the context. So context can mean various different things. It could be the different online platforms that we use to support students' learning, whether or not they are static or dynamic, or even the type of toys that children and parents use when they are playing and talking about various mathematical contexts. So I think about how different tools or different materials may have different affordances and provide different kinds of opportunities for us to think about various different concepts and various different ideas. So that's the influences of context on our thinking. And how does that context influence the way we perceive our environment and the way we act within our environment? So how context influence action and perception, and how that may be related to the way that we think about the world and the learning and the concepts that we have. And then so in the cognition part, I do most of my work in mathematical learning, but I also study a little bit about language development and executive function and self-regulation. And I think about these relations and interactions in a developmental perspective. So how things change over time and how these relations may differ over time. And then so for the first study that we're going to talk about is more focusing on the bottom 2 circle, on the context, how context may influence cognition. And we'll particularly talking about the two games, From Here to There and Dragon Box. So these two different games, how the similarities and differences may have potentially different or the same effects on children's mathematical learning. So here's the paper, examining shifts in conceptual knowledge, procedural knowledge, and procedural flexibility in the context of two game-based technologies. So this work is in collaboration with my colleagues at Worcester Polytechnic Institute, and the paper is published. I think most of you did read this paper for this class. So here is a little demonstration of From Here to There and what it is about. So From Here to There is a game where students work through problems from basic arithmetic to complex ideas like distributions and factoring. So in each of these problems, we will see an initial state that students have to transform into the goal state here. So these two states are mathematically equivalent. And then so students have to find ways to make the center expression look like the goal. And then so they can use the keyboard to factor 6 into 2 times 3. They can also tap, like, for example, the multiplication sign in the middle to multiply numbers. So here we can see that the user is decomposing 6 into 2 times 3. And then again, using the keyboard to factor the 10 into 5 times 2. And then finally, tapping the multiplication sign in the middle to match the goal. And at the end, when students finish solving the problem, they will see a clover board showing the number of clovers that they earn from solving this problem. And we award more clovers for students who use more efficient strategy that involve fewer steps. So this is one way that we encourage students to be flexible in their problem solving and encourage them to find more efficient strategies. Here's another example of From Here to There. So you see that the user dragged the 45 into the parenthesis to distribute, and then to tap the multiplication sign in the middle. Notice that when the user tapped the addition sign between 45x and 450, the expression actually shakes, provides a visual feedback on that this is actually an invalid mathematical action that we cannot perform. We cannot add the two unlike terms together. So the same thing on the other side, we also cannot do this mathematical error. But what we can do is to subtract 45x to both sides. And then we can drag the 45x closer to the other 45x to cancel them out. And then you can see that here the user used the keypad again to factor 450 into 45 times 10, and then do the same thing on the other side, eventually dividing both sides by 45 to reach the goal 10 equals 10. So notice a couple different things here. We do have the step counter, counting the number of transformations students are doing at the step, and the step counter turns red when students take more than the minimum number of steps that they need to solve the problem. So again, this is another little thing that we incorporated in the game to kind of encourage students to use more efficient strategy. All right, so this is From Here to There. And here's an example of Dragon Box and what a problem looks like in Dragon Box. So here in this problem, the goal of the problem is to isolate the box to one side of the screen. So at the end, we should see that there's only this box on one side of the screen and everything is either moved to the other side or canceled out. So here we see that the first thing the user did was to, cancel out the 3 dots on the numerator and the denominator, and then multiply the box by 1. So it's just identity principle that it is equal to itself. And then, interestingly, canceling out the monsters, the positive and the negative monster pictures. On one side, it will turn into a black hole, And then the second thing, the picture of the monster, again, is canceled by its negative. And then we can cancel out the black holes to isolate the box. And then here again, we see that students get awarded 3 stars for solving the problem most efficiently and having the box all by itself on one side. So here is let's see. Here's a little activity for us. Let's get the chat box out in Zoom. And the first question I want to ask you all is to think about, now you see some problems in From Here to There in DragonBox and what they look like. What are some similarities that you notice between From Here to There and DragonBox Algebra 12 Plus? So what are some things you think that they are similar across the 2 games? Go ahead and put your ideas in the chat. Cute pictures. Dragging and dropping part of the equation. That's a great idea. That's right. So go ahead, feel free to keep the answer coming. I'll keep talking. So yes, one of the things that we talked about in the paper is actually this dynamic feature of being able to actively and dynamically manipulate the symbols. I think in both games, we're able to either move the algebraic notations or move the pictures of the boxes. Both of the games are colorful, hopefully engaging. They use rewards, that's right. And From Here to There, they have clovers. And then in DragonBox, they have stars. And yes, rewards at the end. So thank you all for participating, that's great. Now let's think about the differences that the 2 games have. So what are they different on? What are some different features that you notice in the 2 games? Great, thank you, Zoom user. So the first game, that's right, it is grounded in the algebraic symbols. And we didn't see the very first problem of the game, but the entire game uses algebraic notation, either numbers or variables. There's no pictures of dragons in From Here to There. But in DragonBox, the designers actually believe that it is good to hide the mathematics within the game. And then so from the beginning of the game, instead of using numbers and variables, they actually use pictures of dragons. So that's one difference, is the representations and the symbols that they use. And then, yes, so that's right. DragonBox doesn't have the keyboard picture feature. That's a really, really great observation. And I think another difference between From Here to There and DragonBox, this is minimum steps and hints. That's right. And I think, yes, that's one of the differences, that in From Here to There, we have the step counter and like explicitly in various different ways, encouraging students to solve problems efficiently. And that is not as explicit in DragonBox, even though the stars do associate with a number of steps. I think another difference that we said in the paper is the problem solving goal. And this is something that is less obvious, that in From Here to There, you see that the first problem and the second problem, the goal of the problems are not really just trying to get students to combine all the numbers, add all the numbers together, or multiply all of them, or to solve for X. You notice that the goal can be various different things that is just mathematically equivalent to the initial state. So the first goal was, I think it was like 2 times 15 times 2, and the second goal was 10 equals 10. So in a way, the designer From Here to There is trying to get students to think more flexibly and not be kind of fixated on solving for X. But in DragonBox, all the problem is revolving around isolating the box with the dragon on one side of the screen or on one side of the equation. And then, so yes, and DragonBox does have cuter pictures. I would say that, yes. All right, so thank you all for participating in that. And then thinking about how these game features or the problems that we have in these games may influence students' algebraic knowledge. Based on the literatures in algebraic knowledge, people talk about three aspects of algebraic knowledge. The first one is conceptual, and a lot of these conceptual items focus on students' understanding of equivalence. So what are equivalent expressions, or what is the meaning or definition of equal sign? There are also one aspect of algebraic knowledge focusing more on students' procedural knowledge. So how do you solve for X? Or how do you solve an equation or a systems of equation? And then finally, Finally, another aspect of algebraic knowledge focusing on students' procedural flexibility. So their flexibility in problem solving. Can they solve problems in various different ways? And do they realize what is the most efficient way to approach a problem? So in this example assessment item, asking students what's the best way to solve 1/4 times 5x plus 2 equals 8. And the correct answer here is actually, let's see, multiply 4 on both sides first to get rid of the fraction, so we can actually more easily work with the whole numbers in this case. So using the two games and these assessment items, we have two research questions in this study. The first one focusing on the students' performance on different aspects of algebraic knowledge change throughout the intervention, thinking about how do these games improve or may change students' conceptual knowledge, procedural knowledge, or procedural flexibility. And the second question, focusing more on the differences between these two games. So does the changes in these different aspects of algebraic knowledge vary by the games? So for example, do we see that DragonBox actually improves students' procedural knowledge, whereas from here to there improve students' procedural flexibility more? Do we see different patterns between the two games? So the methodology of this study, it's a randomized controlled trial, in other words, an intervention. So there is a paper talking more about the larger study, including a control group. And here we'll only focus on the two game-based study. So I'm happy to talk more about that other paper and the control group later. So in this study, basically students were randomly assigned to either receiving from here to there or DragonBox. They completed a pretest measuring their conceptual knowledge, procedural knowledge, or procedural flexibility in September 2020. So thinking about the context that this is about half a year after the school closures and sudden shutdowns in the US in March 2020. And then so here at the beginning of the school year, students do have the option of choosing to receive their instruction in person at school, or receiving their instruction asynchronous virtually at home. So we do have some students choosing one or the other, and we do include that and account for that in our analysis. After the pretest, students receive 4 30-minute intervention sessions. They log into the game, they solve the problems, and then at the end of the session, they were locked out of the game. And then the next session, when they come back, they start from where they left off and then continue progressing through the games. So they did that for 4 30-minute sessions in the fall semester. And then at the December of 2020, before the holiday break, they receive a mid-test. Again, testing their algebraic knowledge. And then when they come back in January, they continue their game-based intervention, playing the games for 5 30-minute sessions. And then by end of March or early April, they completed their post-test, again, measuring their aspects of algebraic knowledge. So how did they do? So the first research question looking into students' pre-test, mid-test, and post-test scores. Here we see just combining across the 3 aspects of algebraic knowledge, we do see that students seem to improve from pre-test to mid-test, but the improvement seemed to drop from the mid-test to post-test. And then focusing on the conceptual knowledge items and running the statistical models, we found that students improved from pre-test to mid-test on the conceptual items, on their understanding of equivalence. And then the pre-test to post-test improvement is also statistically significant, suggesting that students did improve on their understanding of conceptual understanding of equivalence, and they maintain that gain throughout the intervention period. We see a different pattern of result with the procedural knowledge. Here we see that students did show improvement from pre-test to mid-test, but they also, we also see a drop from mid-test to post-test, and the drop from pre-test to post-test is actually statistically significant. So they are actually doing worse at the end of the intervention compared to the beginning. And we can talk more about why that may be. And we see a similar pattern for the procedural flexibility. We see an increase from pre-test to mid-test, and then a decrease at the post-test. And then here, to answer the second question on do we see the different patterns for different games on the conceptual knowledge, procedural knowledge, and procedural flexibility, we included an interaction term in the regression model. So here the interaction term can tell us whether or not the differences in the mid-test scores, well, the scores on the mid-test, do they differ based on students from here to there versus drag-and-box condition? And what we found is that there are no significant differences between the two conditions on the conceptual items, procedural items, or procedural flexibility items at the mid-test or at the post-test. So this finding suggests that the pattern that we see overall, the increase on conceptual knowledge for the 2 time points, the increase and decrease for procedural knowledge, the increase and decrease for the flexibility are comparable for students and from here to there, and the students in the drag-and-box condition. So in summary, we found that through this study, both from here to there and drag-and-box, they do improve 7th graders' conceptual knowledge of algebraic equivalence. And so suggesting that perhaps the games and their shared features may provide an engaging way to support students' conceptual understanding of algebra. And students also improve on procedural knowledge and procedural flexibility from pre-test to mid-test, but we sadly didn't see this gain sustaining through the end of the intervention. And then so I think that for future studies, we should think about and look into what other ways that we can support and sustain students' procedural knowledge and procedural flexibility. So very quickly, that was the first study focusing on context and cognition. For the second study, I want to zoom into from here to there, and then looking at the other 2 circles, so the perception and actions and cognition. And specifically, I want to think about how presenting problems in different formats or using different symbols, how does that influence students' problem-solving strategy? And we can actually gain insights into students' problem-solving strategy using their actions logged within the technology. So using the log data to look at the influences of perception and students' cognition and problem-solving. So this is a paper again, in collaboration with my colleagues at Worcester Polytechnic Institute on variables versus numbers, the effects of symbols and algebraic knowledge on students' problem-solving strategies. So another activities for you all. So thinking about this problem in from here to there, 3 plus 4 plus 5 minus 3 minus 4 minus 5. We need to transform this expression into 5 minus 5. So what would you do first? What would be your first step? Go ahead and put your first step in the chat. 3 plus 4, thank you, Tomo. That's a great answer, actually. A lot of people actually ended up doing that. I'll show a little bit of data on that. 3 minus 3, that is actually a really smart way to solve the problem. So for the people who answer 3 minus 3 or 5 minus 5. You may notice the structure of combining the opposites or canceling out the numbers that we don't need, right? To save the 5 minus 5 for the goal. And then but when the problems are presented in numbers, there's nothing to prevent you from adding 3 and 4 together, like what Tomo did. But when the problems are presented in variables, now what would you do? What would be your first step? Oh, I like the rearranging. Yes, that is actually a really cool way that to put the numbers that you need to cancel out together. So thank you for the person responding A minus A. Yes, so here, when the problems are presented in variables, we can't just add A and B together, but we really need to figure out the patterns and the structure here to combine A and minus A and B and minus B. So everything that students are doing in from here to there, we actually have the log data. So we can see the moment-to-moment action, the timestamp, and how long they take between each step. So here's a problem-solving process on a more complex problem, how students solve the problem. And then here's a form of the log data, seeing that student first, the initial expression looking like this, they take 3 seconds to multiply the 7 with the 7 in the denominator to get to 1, to subtract 6 and 6 to get to the 0 in the middle, and then finally to divide 5 and 5 to get to the 1 at the end to reach the goal state. And then from here to there, any mathematically valid action could work. So like what Tomo did, adding 3 and 4 together, technically you can do that, even though it may not be the best strategy to do that. So some people may use really efficient strategy and other people may not. And we can actually visualize the variation within the sample using a Sankey diagram and looking at the flow and the path from the beginning of the problem state and the various states that people come up with and how many people go from one state to the other state. So we can really see what is the most common or most popular steps that people take throughout the problem solving process. So all the really cool things that we can do with the log data and from here to there. So using these data and from here to there, we ask first, does the student's strategy efficiency as measured by their number of problem solving steps actually vary on the problems presented in variables versus numbers? So do we see different strategies depending on the problem features, so the symbols that they are presented in, even though the structures are the same? And then second question we ask, does the effect of symbol on student strategy efficiency vary by students' algebraic knowledge? So here, this is another interaction that we wanted to see. So do we see differences in the patterns of results based on students' algebraic knowledge? So for example, do we see that students with higher algebraic knowledge, are they more efficient on solving variable problems, whereas students with lower algebraic knowledge, are they more efficient at solving numerical problems? So the data set came from the same intervention study, the same sample of students, but we have a smaller sample because these problems that we designed to answer the variable versus numbers problems are embedded in the middle of the game. So only 445 students who get to this point of the game. And then you can see a list of the problems that we designed and included in the analysis. So we have the numerical form of the problem and the variable form when the opposites are next to each other or they are further apart, like the problems that we tried earlier. There are simple problems that only involve addition and subtraction, and there are more complex problems, also including multiplication and division. So there are a variety of problems, but all of them focusing on this idea of combining the opposites, and do students notice this pattern in the problem structure? And we found that when we look at the simple problems, we see a main effect of algebraic knowledge. So this is the slope, the negative slope that we see in this graph. So the x-axis is the algebraic knowledge score. They're centered, so 0 is the average score. The y-axis is the total number of steps. So more steps means less efficient strategy. And here we see that for students with lower algebraic knowledge, they take more steps to finish the problem, suggesting that they're using less efficient strategy. And we see here for students with higher algebraic knowledge, they're using more efficient strategy involving fewer steps. So we see a main effect of algebraic knowledge. We also see a main effect of symbol. That's the blue line for variable being on top of or being above of the red line for numbers. So students are taking more steps on variable problems compared to numerical problems, at least in the simple problem context. We don't see different patterns of results. So more steps on variable problem compared to numerical problem, that's the same for students with higher or lower algebraic knowledge. So the pattern is the same for the two groups, or for the students at different levels of algebraic knowledge. But on complex problem, we actually see a different patterns of results. Here, we see that for students with lower algebraic knowledge, they are taking a lot more steps on variable problems. So they seem to be struggling with variable problems. They are actually more efficient on numerical problems. But for students with higher algebraic knowledge, they are taking fewer steps on variable problems. So suggesting that perhaps they are noticing the patterns, the opposites and inverses within the problem structure in variable problems in particular. The slope here, we do see the steep negative slope for variable problems, but the slope for numerical problems, this is actually not statistically different from 0. So we can interpret this as that for numerical problems, we actually don't see differences between students with higher versus lower algebraic knowledge. So the differences that we are finding is on the variable problems. And now coming back to the problem that you all solved on the first step, what did you do? Here's what we find with the students in our sample. So when the opposites are next to each other, and when the problem structure is fairly simple, only involving addition and subtraction, we see that most students, 97, 99% of the students, they do combine the opposites immediately. So either doing 9 minus 9 or a minus a or 7 minus 7 or x minus x, y minus y, z minus z. So they're doing that. So that's great. When the opposites are far apart, we see that a lot more students are combining the opposites when the problems are presented in variables. So they do notice the structure and combining the a minus a or moving them closer together. So 94, 95% of the students are doing that. But when the problems are presented in numbers, actually only 17% of the people, unlike you all, thinking about combining 3 and minus 3 together immediately, most of the people, 80% of the people, they actually do what Tomo did by combining 3 and 4 on the left side of the equation. So they start from left to right, suggesting that they may not notice the pattern, the opposites within the expression, and they are just jumping into the problem, immediately trying to perform some operations and actions. And then with more complex problems, again, we see this effect of adjacency when the numbers to be combined are closer together. Most of the people do actually end up combining those numbers together. So 1/7 and 7, or 6 minus 6, or 5/5, they do that as their first step. But when the problem is so complex and when the opposites and inverses are far apart, only about 20 to 25% of the people are doing that. And it doesn't matter whether or not the problems are presented in numbers or variables. So a quick summary for this study, we found that students with higher algebraic knowledge, they tend to be more efficient on simple problems. So that's the negative slope that we see in the simple problems involving only addition and subtraction. But on complex problems, we see that interaction. So students with higher knowledge, they are more efficient on the variable problems compared to the numerical problem. But we see the opposite for students with lower algebraic knowledge. So for these students, they are actually less efficient on the variable problem compared to the numerical problem. And then so we think one of the suggestions that we have based on this finding is that maybe providing students with variations of the problem structures and using different symbols, not always using numbers, maybe providing some variables or some mixtures of them may help them notice structure and feel more comfortable at solving various different types of problems. And then the log data within the games and the technology can actually help us gain insights into students' action and cognition. So a quick take-home message that I would like to share and thinking about going beyond the findings and results that we have from these two studies. What are the bigger ideas that we can take home from these two studies? The first one is to think about going beyond testing the efficacy of technology and to think about identifying the design features that actually make them effective. So if one game is improving students' learning or algebraic knowledge, maybe go a step further and not just think about this game is great, but think about what are the active ingredients? Why is this working? What is making it effective? And then so we can use the knowledge that we learn from the game design features to help us design other games for other learning domains. I think some of you are interested in that. A second point that I want to make from study 2 is to think about collaborations and using log data to study students' thinking and potential misconceptions. So here, I think that log data can provide really fine-grained and rich information that help us make students' thinking feasible. And then so it would be great if we can actually, when we are designing tools, think about the type of data that you want to record, the type of actions that you want to capture and to analyze later to actually better understand students' thinking process through their actions within these tools. So with that, I would like to thank you all for your attention and thank you, Tomo, for having me. And then, of course, I'll thank the children's parents, teachers, staff, and schools who participated in this research and make all of this project possible. And then my collaborators and labs and students for working on these projects and the various funding sources. And I'm always happy to talk about this work or other parts of my work. So feel free to email me, follow me on Twitter, or visit my website to learn more about my work. And then here are just some of the collections of arts and little pieces of notes that I get from participants throughout the years and my writing buddies, my 2 cats, as I work on these papers. And then I'll open it up for discussion. Happy to talk about anything that you all want to talk about. And here are just some of the points that I got from the questions and comments that I read and Tomo sent to me. So yeah, that's it. Thank you all.
Thank you so much, Jenny, for the wonderful talk with interactive activities. And then I really enjoyed these two studies.